Hi everybody, I hope this video finds you well. In today's video, we're going to be taking a look at some examples going through the sort of theory that we developed at the start of section 8.2 here. So, if you'll remember from the end of the previous video, we came up with this summary that talked about what to do in the different situations with the roots of the auxiliary polynomial for a polynomial differential operator. So, remember that we said that if we had a polynomial differential operator, P of d of y equals 0, so it's a homogeneous equation. And then we said that if we had the auxiliary polynomial and it has roots r with multiplicity m, then there are sort of two cases. Case 1, if you have real roots with multiplicity m, then you're going to get the following linearly independent solutions to the homogeneous equation. E to the rx, x, e to the rx, all the way down to x to the m minus 1, again, m being the multiplicity, times e to the rx. And of course, this is going to give you a list of m linearly independent solutions, which matches the multiplicity. Case 2, if the root you get is complex, then the conjugate will also be a root with the same multiplicity. So if the root r is complex a plus bi and it has multiplicity m, then a minus bi will also have multiplicity m. And we will get the following linearly independent solutions to the homogeneous equation: eax cosine bx, eax sine bx, then x eax cosine bx, x eax sine bx, all the way down to xm minus 1 eax cosine bx, xm minus 1 eax sine bx. And of course, because these were two roots with multiplicity m, that's 2m overall, this gives us 2m linearly independent solutions here. So all of this was relatively abstract. So in this video, we're just going to look at several examples of using these results, these two cases, to talk about the general solution of different constant coefficient homogeneous equations, and also the particular solution to a couple IDPs. So let's get in and take a look at those examples. So for our first example, we'd like to find the general solution to this constant coefficient homogeneous differential equation. If it helps, you can definitely think about this in terms of the differential operator. This is equivalent to d cubed minus d squared minus 6d of y equals 0. And of course, notice that since it is equal to 0, it is homogeneous, so our approach is going to sort of work here. The auxiliary polynomial, if you prefer to think about it in those terms, is P of r is r cubed minus r squared minus 6r. If we set that equal to 0 to try to find the roots here, well, it's a cubic, which is not our favorite thing to solve, but we can factor an r out to get r squared minus r minus 6 equals 0. And then we can factor that a little bit more. Looks like r minus 3 and r plus 2 equals 0. So it looks like we would get the roots of r equals 0, r equals 3, and r equals negative 2. Each of these guys with multiplicity equal to 1. Each root only shows up once. All right, so let's go ahead then and put that into sort of those cases. If we look back here, all of these are real roots and they all have just multiplicity 1, so we'll just be using the form ERX. So what this tells us is our sort of general solution is going to be a linear combination of the solutions that come from each of these. So it would be some constant c1 e to the 0x plus some constant times our result from here, which would be c2 e to the 3x plus, and then some constant times the solution that comes from here, c3 e to the negative 2x. So our general solution is anything that looks like that. Now, of course, e to the 0x, we know that that's just going to be a 1. So this is really c1 plus c2 e to the 3x plus c3e to the minus 2x. That is our general solution to that constant coefficient homogeneous differential equation. Notice it also makes sense. We said that the solution space to an nth order homogeneous linear differential equation is n. This is a third order. This has 3 free parameters, so it is 3-dimensional. Makes sense there. So there we go. There's our general solution to this constant coefficient linear differential equation. Okay, Let's move on to another example, see what happens when we have some repeated roots or some complex ones. So this guy, we have it already written in terms of the differential operator. So it's actually already written in sort of a factored form. D minus 3 times d plus 4 cubed of y has to be 0. The auxiliary polynomial here, p of r, would be r minus 3 and r plus 4 cubed. If we set that equal to 0, r minus 3, r plus 4 cubed equals 0. Should be pretty easy to see that we have a real root, r equals 3, and another real root, r equals negative 4. This guy is multiplicity 1. That root only shows up once, whereas this guy is multiplicity 3. All right, so we can go ahead and then talk about the general solution from this. So the component that comes from this, r equals 3, let's go check our case. Well, it's a real root, so we should just be getting e to the rx. So some linear combination of that, so c1 e to the 3x plus, then we should be getting 3 linearly independent solutions from r equals negative 4. Since we have a repeated root, notice we are going to have e to the negative 4x, x e to the negative 4x, and then x squared e to the negative 4x, because we will go all the way down to x to the m minus 1. The multiplicity is 3 here. 3 minus 1 gives us 2. So we should have c1 plus c2 e to the negative 4x plus c3 x e to the negative 4x plus c4 x squared e to the negative 4x. So notice that this e to the negative 4x sort of expression shows up 3 times for the multiplicity, but each time, since it is repeated, we have an x and then an x squared there. So this gives us something that has 4 unknown constants in it, or 4 free parameters, telling us that this is a 4-dimensional solution space, which makes sense because if we multiplied all this out, we'd have a d cubed and a d, meaning the highest order derivative was a 4th derivative, so it is a 4th order differential equation. Makes sense that we then have a solution space that has 4 free parameters. Let's go ahead and try another example where we actually have some initial conditions, making it actually an IVP. So let's see if we can find the unique solution. Notice we just say the solution because we know that any linear differential equation has a unique solution. That's the existence and uniqueness theorem for linear differential equations. And of course, constant coefficient ones are going to always be linear. So if we convert this into a differential operator form, this would be d to the 4th plus 16d squared of y equals 0. All right, the auxiliary polynomial would be p of r equals r to the 4th plus 16r squared. Let's set that equal to 0. So 6r to the 4th, 16r squared equals 0. We can factor out an r squared and get r squared plus 16 equals 0. Now we know that this doesn't break down any further over the reals, right? This is an irreducible quadratic in terms of real solutions, but this does have some imaginary solutions. So we can see that we have r equals 0. That's a multiplicity 2 root. And it looks like we have r is plus or minus 4i. Now notice that there's 2 roots there, 4i and negative 4i, and each of those are multiplicity 1 because there was only one factor of this r squared plus 16. All right, so let's talk about what the general solution would look like. So the general solution here, y equals, so from these guys, we would be getting c1 e to the 0x plus c2, then x e to the 0x, because this guy has multiplicity 2, and the root is r equals 0, so 0x and 0x. Then from these guys, what we'd be getting is we'd be getting plus c3 e to the 0x, because there is no real component to this, cosine 4x plus c4 e to the 0x sine 4x. And the sort of key thing that you guys want to recognize here is we're treating this as 0 plus 4i. All right, so the 0 is the real component, so we're getting e to the 0x on those, and then the sine and cosine 4x. And again, that's making use of this case 2 that we have here, where we said if we had a plus bi and a minus bi, then we're using cosine bx, sine bx, and since they were multiplicity 1, we don't have anything that's like x times that. Okay, so there's our general solution. We can simplify that a little bit. That looks like it's actually c1 plus c2x plus c3 cosine 4x plus c4 sine 4x. Now, we would like to know these constants based on these initial conditions. So let's go ahead and take a couple derivatives of this. We get that y prime would be c2 minus 4c3 cosine, sine 4x, excuse me, and plus 4c4 cosine 4x. Second derivative would then be negative 16 c3 cosine 4x plus 16 plus negative, because we get a negative there, negative 16 c4 sine 4x. And then one more derivative would give us 64 c3 sine 4x minus 64 c4 cosine 4x. Okay, so now we can plug in our initial conditions there and get some equations that we can try to solve there. So y of 0 equaling 1. That looks like that tells us that c1 plus c2 plus plugging in 0 in here is going to be cosine of 0, which is 1, so plus c3. And then, of course, this is going to be plus 0 c4 is equal to 1. Then we also have y prime of 0 is supposed to be 0, according to this. Y prime 0 is 0. So it looks like we should have that c2, 0 c1, because there's no c1 left, so 0 c1 plus c2. Plugging in 0 is going to zero this out, but it looks like we're going to get 4c4. So plus 0 c3 plus 4c4 is supposed to be 0. Then y double prime at 0 is supposed to be 1. So if we're plugging in 0 into this, it's going to zero that out, but we will get this guy. So that looks like we're going to get 0 c1 plus 0 c2 minus 16 c3 plus 0 c4 is equal to 0. And finally, y triple prime at 0 is supposed to be 0, according to this initial condition right there. So that tells us plugging in 0 here is going to zero that out, but leave this guy, which is going to be 0 c1 plus 0 c2 plus 0 c3 minus 64 c4 is supposed to be 0. And my mistake back here, this guy should be equal to 1. Yeah, there we go. All right, so we can solve some of these. These guys, we can just get some things right away. This guy implies that C3 should actually be negative 1 over 16. And this guy implies that C4 should actually be 0 there. Now with that, we can sort of grab these guys. Over here, I can just turn this into C2 plus 4 times 0 equals 0. So that looks like C2 is supposed to be 0. And then if I grab this guy, that looks like, let's see, we should have C1 plus 0 minus 1 over 16 is supposed to be 1. So that implies that C1 is supposed to be 17 over 16. So it looks like our unique solution is actually supposed to be y is 17 over 16, because that's our c there. Our c2 is supposed to be 0, so we don't need that. Our c3 is supposed to be negative 1 over 16, so we get negative 1 over 16 cosine 4x. So minus 1 over 16 cosine 4x, and then our C4 is 0, so we don't need any of the ones from the C4 sine 4x. So there we go. The unique solution to this IVP is this guy. If you want on your own, you can confirm that this satisfies the differential equation. In other words, if you take the fourth derivative of this and you go ahead and you add 16 times the second derivative, you will go ahead and get 0. And it also has these 4 initial conditions. If you plug in 0 into this, you will get it equal to 1. If you take its derivative and plug into 0, you will get 0. If you take its second derivative and plug in 0, you will get 1. And if you take its third derivative and plug in 0, you will get 0. So this is our unique solution to the IVP. So notice that when I was solving this back here, if we had had messier equations and we hadn't gotten so lucky that we just got 2 of them, we would have been right to set this up as a 4x4 system and just go ahead and directly solve it. And we know it will have a unique solution whenever you go to do these C1, C2, C3, C4. You know there's going to be a unique solution because your general solution tells you the basis elements, meaning since it's a basis, there's always going to be a unique representation, a unique solution here. All right, let's take a look at one more example, sort of going back to talking about general solutions, looking at a very sort of high order constant coefficient one to make sure we're comfortable with all the different cases and how they interact. All right, so as our last example here, we're going to go ahead and find the general solution to this constant coefficient homogeneous differential equation. A quick check should show you that this is order 1, and then 3, and then 4. So this looks like an 8th order differential equation that we're doing. So if we were actually to write this out, there would be an 8th derivative involved in it. But instead, we should be able to do this pretty easily using our different cases, understanding the roots and the multiplicities. So this is already written in the differential operator form, so we can write the auxiliary polynomial. Looks like it's r minus 5, r cubed, and r squared plus 2r plus 10 squared. If we set that equal to 0, r minus 5, r cubed, r squared plus 2r plus 10 squared equals 0. Should be pretty clear that this guy gives us r equals 5, a real root with multiplicity 1. This guy should give us r equals 0 with multiplicity 3. That's going to be a real root but multiplicity 3. And this guy, well, we know that it's going to give us multiplicity 2, because it's repeated twice, but we need to figure out what the roots are in here. Doesn't seem to factor cleanly, so we can go ahead and maybe do this a little off to the side or something. Go ahead and do that in green. So let's grab this guy here. If we have r squared plus 2r plus 10 equals 0, obviously, if we don't see an easy factorization, we just use quadratic formula. We get r is negative 2 plus or minus square root 4 minus 4ac, which is 40, divided by 2. Looks like r is going to be negative 2 plus or minus square root negative 36. Looks like we're going to get a complex conjugate pair. And looks like we're going to get negative 1. Not yet. We won't do that division yet. Negative 2 plus or minus 6i over 2. And looks like it's going to be r equals negative 1 plus or minus 6i. But remember, this guy was repeated twice. So this complex conjugate pair is actually has multiplicity 2 here. So we've got 4 real roots and 4 imaginary roots. We've got 3, or technically 4 distinct things, but 2 of them are a complex conjugate pair there. Okay, let's talk about what the general solution is going to look like, and I'll sort of use the colors to match where each component is coming from. So the general solution here, y equals, it's going to have 8 different unknown coefficients because we know that the solution space is a vector space of dimension 8 because we're working with something that is order 8. So what do we get first from this, this blue component here? Well, if we take a look at this guy right here, r equals 5, multiplicity 1, the first piece that we should get is c1 e to the 5x. right? No other components because it's got only multiplicity 1. The root was 5, so we have 5x there. For this guy, we would have 3 pieces that come from this. So c2 e to the 0x plus c3 x e to the 0x and c4 x squared e to the 0x. Notice that we get the solution itself multiplied by x and multiplied by x squared because we have multiplicity 3. We always go up to x to the m minus 1, and m minus 1 in this case is 2. From these guys, right, we see that the real component is -1 and the imaginary component is at 6i. So in that case, let's go ahead, we'll do our green here, put this on the next line, plus c5 e to the -x cosine 6x. That's our A and our B there. Then plus c6 e to the -x sine 6x. So that's how we deal with the complex conjugate that we got there. Now, since it has multiplicity 2, we're going to repeat both of these solutions, but with an extra factor of x in there. So we'd also have plus c7 x e to the -x cosine 6x plus c8 x e to the -x sine 6x. So there we go. We get one solution, one linearly independent solution from this guy with multiplicity 1, 3 linearly independent solutions from this guy with multiplicity 3, and we get 4 solutions here from this complex conjugate pair with multiplicity 2. It's a pair with multiplicity 2, so that's 2 times 2, giving us 4 linearly independent solutions there. Could we clean it up a little bit? Sure, we could say that y overall is c1 e to the 5x plus c2 plus c3x plus c4x squared plus c5 e to the -x cosine 6x plus c6 e to the -x sine of 6x plus c7 x e to the -x cosine 6x plus c8 x e to the -x sine 6x. And there we go. There is our general solution to this 8th order constant coefficient homogeneous equation. So hopefully these 4 examples give you guys a little bit more understanding of what those different cases were that we developed in the previous video. In our next video, we'll be moving on into section 8.3, seeing how this approach can be applied to non-homogeneous constant coefficient linear differential equations.